Hey, Kenneth.
Right.
Still waiting on Brandon said that he was gonna join, but uh
Okay. Yeah, I know Gus isn't because I talked. He said he wasn't gonna this
yeah,
week, but next week he will.
so
He's too good for this now that he's half.
he earned a break for a day.
Yeah.
He said that he might uh join next week though, but
Yeah.
while we wait, we can give him like 5 more minutes. Do you have any questions for me? I know you've been studying. Do you have anything?
No, I mean the stuff like some of them I was like got wrong. I'm like, why? And then I popped in my head today. I'm like, that's what I did wrong.
Okay. For the
Like some of the stuff is just like, like one of them it was like you're landing on 2-6 or whatever, and like the wind is this, like what should you do? And I was like,
Mhm.
I'm what I figure I'm gonna do is write a little compass because I'm like, oh, like or 1-7 or whatever it was. I'm like, oh, it's just one tick over here, and like I was on like 180 being an idiot. I'm like, I need to be over more,
Yeah,
like
the
just
thing
stuff like
about
that.
the
I
thing
think
about the
what it
runway
is
is,
was the little like half compass thing on the ruler, like
yeah,
270s right in the center. I think that's what like got stuck in my head when I was doing something earlier. I'm like, oh yeah, that's where 270 is. I'm like, no,
yeah.
it's not.
For
So
for the wind and the runways, if you can just remember, just take the runway number and subtract it from the wind, or take the wind and subtract it from the runway, whichever runway has the smallest
yeah,
difference,
I
that's
know
going to
how to
be
do that stuff
okay.
since I'm flying. So that's not, I was just being an idiot, is all it
Okay.
was.
Okay. Well,
Like,
as long as you know
so
what your mistake
yeah,
was.
some of the stuff I know because of actually flying. I'm like, oh, I already knew this, but it's
Yeah.
like, I don't know, just some of the dumb mistakes I made. I'm like, really? Like, what?
Yeah. Well,
So,
as long as the new questions you're seeing aren't completely new topics, because then that's
like, let's see. One of them earlier was, what was it? It's like in an emergency flight requires immediate action. The pilot in command may. It's like I know to deviate, but I figured like, oh, yeah, like to notify them or something, like. So it's like I knew I was also leaning towards that. I'm like, no, but I think you probably have to report it.
yeah.
So it's just little, honestly, stuff if you really didn't know, you would look up anyways. Like,
Yeah.
uh, I mean, some of the stuff I get wrong is like, when should you notify them after you get a DUI and blah blah blah, or like
Yeah.
drugs and stuff. I'm thinking like, I guarantee no freaking pilot knows that. They're gonna be like, well, let me go look it up.
Yeah, that's just stuff
Like,
you have to memorize for the written. So,
yeah. So I don't know. Some that kind of stuff. It's like that's really not necessary because that's lookup material. But like when it actually comes to the flying stuff, that makes sense. But so that's all. It's just having to know stuff that really isn't that important as far as flying goes. Like, yeah, it's important, but to remember it, not really.
yeah.
So, because you're not going to be in the middle of flying and be like, shit, did I remember to report this marijuana violation that I just had?
Yeah.
Like you're going to look it up just to make sure.
Just
So,
stuff they need to cover for the written. That's it.
yeah, yeah. I mean, one it was talking about a dust devil, crossing the runway. I'm like,
Yeah.
well, I just go around, and I'm like, yeah, I was right. So, like, but yeah, I think some of it is just like, I don't know, like what would be the safest option? That's like with that one, it's gave you choice of go around, continue landing as normal, or land past the dust devil. So I was like, well, the safer option to me would be go around, and then by that time the dust devil's probably gone.
Exactly.
So I mean, that's some of them. It's just like, what's the safer option?
Yeah.
So
Is your test tomorrow then, Kenneth?
yeah,
Okay.
I'm taking
yeah.
mine tomorrow as well.
Where are you taking yours at, Brendan?
OSU.
Okay. Are you at OSU too, Kenneth?
Yeah, what time's yours?
I think mine's at 2 o'clock.
Hey, I'll see you there. They mu
Cool.
they must just leave multiple openings for the same time. Because when I
Yeah.
saw it, I was like, oh, there's only one available time. Oh, lucky me. But
Yeah, I
I'm
booked it
guessing that's
last.
maybe, like you said, they don't have a lot of openings at OSU because they give them more to the students, but maybe from that 2 to 4:30 block, it's just open for everyone, you know?
Yeah, I don't know what the deal is over there. I don't know.
Because the
Uh,
only option was I told you it wouldn't let me choose the one you recommended, and it's like I'm not traveling 45 minutes one way.
yeah, isn't that where
That
Gus
was
went though? Didn't he go down to Groveport or
um
whatever? I think that's what he did.
yeah, I think it was the what was it? The where was that one? It was the
It's in Groveport. It's down by
yeah,
Richard
the
Miner.
Groveport one. Yeah, I think that might have been the one he did. So, but like for me, I'm like that's like it'd be an hour and a half round trip.
Yeah.
I'm like that's
Well, don't
with
forget tomorrow to
OSU.
take your endorsement
Yep,
and
I got it
your
here.
photo ID
Yeah. Yeah.
and
Well,
anything else that you'll need. So your E6B.
yep.
Yeah,
Make sure
leaving
you
the
have
paper one
address.
here.
Yeah.
We'll probably bring, what is it, three extra triple A's just in case.
Yeah.
Then I'll be wishing like, damn it, I don't want to hear it, Gus, you and your little paper one. My battery's died.
Okay, let's get started here. This is all who's joining us today. I'm recording it for the other people that can't get to it, and I can send you guys a copy when we get done with this. That way you have it. But we're gonna do chapters 4 and 5 today. The first chapter, the first chapter, chapter 4, is principles of flight. So this is going to talk about a little bit about the atmosphere and then about density and pressure and that stuff. It's all review, obviously, from what we learned in ground. But the first concept they talk about is the concept of air as a fluid. So the atmosphere behaves in the same way as a fluid, takes the shape of its container. So, right, that's going to be the atmosphere is contained by Earth's gravity. Basically ends up being a circle around the Earth that gets has less pressure as you go up. Um, they say that a fluid generally does not resist deformation. You know, that's the whole taking the shape of its container. So if you move it from one container to another, it's not going to try and retain its shape like a solid will. And the small resistance it does offer is called viscosity. I don't know why the PHAC wants to talk about viscosity. But this is, I just followed literally the headers in the PHAC. So the next thing they talk about is viscosity. And if you don't know what that is, it's basically how runny a fluid is going to be. So things like honey have a very, 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 very high viscosity. The molecules in honey will stick together very, very well. Things like water have a lower viscosity. And according to this chart, looks like methanol has like the lowest viscosity. It's nice and runny. So the only time that you're really in flight training, especially going to hear about viscosity specifically, is talking about the engine oil. And the reason for that is
Yeah.
um, the oil is more viscous or thicker when it's cold. So that's why, like, if you read a POH or something, they'll have like warm up times for the engine. So when you start an engine, you'll want to sit there and leave it at 1,000 RPMs or whatever they prescribe for X amount of minutes or until the oil reaches X temperature. And that just makes sure that you're not pushing this thick, not very viscous oil through the engine at high power settings, which can damage it. Um, this is another reason. It's half the reason why sometimes when you start up, it's a good idea to lean the mixture out. By leaning the mixture, the engine's going to run a little hotter. It'll help the oil heat up quicker, and it also keeps you from fouling your spark plugs, which we'll talk about when we talk about systems. Next thing they talk about is friction. So it is impossible to create a perfectly smooth surface. Every piece of the airplane creates friction with the air. The picture down here is a zoomed in photo of the wing there. You know, it looks smooth, but microscopic. There's little ridges. Um, what this does for the airplane, besides being a form of drag, is that the particles very, very, very close to the surface of the airfoils have almost no relative motion. We call this the boundary layer. So the boundary layer is the layer of air that is very close to the surface that does not move for the most part relative to the air around it. So when you hear the term boundary layer, especially when you're talking about stalls, you'll hear the separation of the boundary layer, and that is happening during a stall. That boundary layer becomes no more.
So that boundary layer, like could you think of it as like almost like a blanket that's like of air that just doesn't move? It's so tight to the wing then.
Yeah, pretty much. It's stuck in these, they would be, the particles would be stuck in these ridges pretty much. And they create kind of a static layer of air on the airfoils. And I don't really know, I don't know if it really does anything, quite honestly. I'm sure that it has some sort of effect, but the only time you're going to hear about this boundary layer for the most part is when they talk about stalls, because when you stall, you exceed that critical angle of attack, and that boundary layer finally separates because there's not enough air making it over the top of the wing to create a boundary layer for you.
Cool.
Next thing they talk about pressure. They define pressure as the force applied in a perpendicular direction to the surface of an object. So normally we're measuring pressure in pounds per square inch, right? So this is what you're going to pump your tires up to, whatever PSI. An object completely immersed in a fluid, and in this case, the atmosphere, will feel pressure uniformly around the entire surface of the object. So, right, we're feeling the atmospheric pressure all around our body, on my arm, on my leg, not just on the top of my head. And if the pressure exerted on one surface, and this is what you really want to take away from this, if the pressure exerted on one surface of an object becomes less than the pressure exerted on the other surface, the object will move in the direction of lower pressure. So this is the important thing to remember when we're talking about basically when we're talking about performance and when we're talking about systems later, is that pressure in nature always wants to equalize. Okay, so if you can remember that the flow of pressure is always going to be from high pressure to low pressure, you can think your way through a lot of problems that we could be in. This is just showing, this is the ideal gas law. But what it's showing and why I put it in here is basically you have the same amount of molecules, I assume. I didn't count them, but let's just say for the sake of the demonstration, it's the same amount of molecules in both of these. And the only thing you're changing is the volume of the container. So how much space there is. You're increasing the pressure, you're increasing the force exerted on this stopper here. And if you were to let that stopper move, the molecules would spread out, creating a larger volume. What they're doing is moving from this is an area of high pressure to this is relatively low pressure, because in theory, there's no molecules here. They're trying to move and to occupy that space, right? So they're trying to get to equilibrium. So just remember, that's the most important part of when we talk about pressure. Next, they talk about the atmospheric pressure, right? Air has mass, therefore it's affected by gravity. The Earth's gravitational pull creates the container that is the atmosphere. We talked about this in class, but under standard conditions, the atmospheric pressure at sea level is 299 or 2 inches per mercury, 14.7 pounds per square inch, or 1013.2 millibars respectively. So you go overseas, they actually will end up using millibars. In the States, we use inches of mercury. 14.7 psi is just used in the PHAC. I don't know why, but they do list it. And then I put in here standard temperatures 15 degrees Celsius or 59 degrees Fahrenheit. As you guys know, atmospheric pressure decreases as the increase in altitude, with the pressure at 18,000 being half of standard. So on a standard day, you go up to 18,000, you've already passed through half of the atmosphere. Half of the atmosphere's mass is contained below 18,000. The atmosphere, I think, technically goes all the way up to like 600,000 feet, something like that. So it's crazy how much the atmosphere is concentrated in that first 18,000 feet. As you remember from class, we have lapse rates. So the lapse rate is going to be the average change in whatever we're talking about. And we use it at, we talk about it in terms of thousands of feet. So the average pressure lapse rate is 1 inch of mercury per 1,000 feet. So every 1,000 feet you go up, you're supposed to lose 1 inch of mercury. Now, in theory, does that happen? Not in my experience, right? Because we've talked about this a few times. That would mean the pressure at Delaware, pretty much, because it's about 1,000 feet above sea level, should always be 289 or 2, and I've never seen that before. But that is, we base observations and stuff like that off of this average pressure lapse rate. The average temperature lapse rate is 2 degrees per Celsius, 2 degrees Celsius per 1,000 feet. Then we have what are called the dry and the wet adiabatic lapse rates. The dry adiabatic lapse rate is closer to 9 degrees Celsius per 1,000 feet, and the wet adiabatic lapse rate is between 4 and 9 degrees Celsius per 1,000 feet. The difference in these is because dry air, or because wet air holds heat better, right? Remember from class that wet or water is a great heat sink. It holds heat very well. It's harder to change the temperature of water. So its lapse rate is less than a dry adiabatic lapse rate, which would be completely dry air without any moisture in it. I don't know how you take the dry and the wet adiabatic lapse rate and you get 2 degrees as the average temperature lapse rate, but that is what the temperature lapse rate is, what they say the average temperature lapse rate is. What that means for us guys is that as you go and look at the weather and you're trying to determine if the atmosphere is stable or unstable, if the temperature is changing at a rate greater than 2 degrees per Celsius, 2 degrees Celsius per 1,000 feet, that's considered an unstable atmosphere. That usually means that you're having more turbulence and the possibility for severe weather is greater. I put in here the picture on the left. This is just a heat chart of the atmosphere. What you'll see, you'll notice that the left side, the y-axis is in kilometers, the right side it's in miles. The temperature decreases steadily to the top of the tropopause, the top of the bottom of the tropopause, or yeah, to the bottom of the tropopause. I'm sorry. The bottom of the tropopause varies, but it's about 36,000 feet. And then once you get to the tropopause, you actually, as you go up, the temperature stays the same. Then when you get into the stratosphere, it starts to increase, and then you can see how it goes the rest of the way. But that's just interesting. It's a good way. You know, when you get to your commercial, you might get a question about, you know, what about the temperature in the tropopause, how you know you're in the tropopause. You keep climbing and the temperature stays the same. Pressure altitude. So you had a question about this last week, Kenneth. It's always good to cover because this is something that confuses people and is confusing, can be confusing for a long time. So pressure altitude, guys, is the height above the standard datum plane, which a theoretical pressure of 299 or 2 exists. So that the height above the standard datum plane is sea level, right? Or I'm sorry, the standard datum plane is sea level. So we're trying to find the height at which on this specific day, 299 or the pressure 299 or 2 exists. So you can do this 2 ways. You can either set the altimeter 299 or 2. If you're sitting in the airplane and you have an altimeter in front of you, you can do that and you'll find the pressure altitude. Or you can also compare the current altimeter setting to 299 or 2 and do the math, which is what I showed you guys in class. So remember, you always put 299 or 2 on top, and then you subtract the current altimeter setting. You take that number and you times that by 1,000 because it's pretty much always going to be a decimal. Times it by 1,000 because that is related to our lapse rate. Then you take that number and you add that to your field elevation. And that'll give you the pressure altitude. Don't forget, the most common mistake is going to be that normally that number is going to be negative. And when you add a negative to the field elevation, it's just subtraction. Okay. So a high pressure, like a high altimeter setting, is going to cause you to have a negative number, and you'll subtract that from your field elevation, which should make sense because higher pressure relates to better performance, which would mean a lower elevation. The reason that we need to know about pressure altitude is because it's used to help calculate airplane performance. And a helpful way to think about pressure altitude is as altitude corrected for non-standard pressure. And the reason that I say that is because when we get to define our next term, density altitude, what the FAA defines that as is pressure altitude corrected for non-standard temperature. So this is going to be the altitude the airplane feels like it's flying at. This is critical for determining how the airplane is going to perform, okay? So a high density altitude, if we go out and we say the density altitude is like 8,000 feet, that's a bad thing. The airplane, you don't want the airplane to feel like it's flying at 8,000 feet when you're only at 2,000. Low density altitude is a good thing. So if you sometimes in the winter in Ohio, you go outside and it's negative 800 density altitude, that's a great thing. That means that the air is going to be nice and dense. And we know that the airplane loves dense air. Density altitude is affected by changes in pressure, temperature, and humidity. Those are the three biggest factors that change our density altitude. On the left, you guys are familiar with this chart. This chart is one way to find the density altitude. The other way is just to use, you guys both have the E6B, so I'm 99% sure the electronic E6B can calculate the density altitude for you. So you can do that. I used to always just Google it and use a calculator on the internet. So effects of temperature on density. Okay, so to think through temperature, pressure, and humidity and how they relate to how they impact our performance, whether they make it better or worse, all you need to remember or all you need to know is how those things impact the density of the air. A increase in density is a good thing for performance. A decrease in density is a bad thing for performance. So like when we talked about in class, temperature on a particle level is just measuring the amount of collisions between the molecules in a substance. So in this case, it'd be the atmosphere. So when you have a really high temperature, the molecules on the right are very active. You can see these lines that are drawn are larger, symbolizing that they're moving more. What this means is the density is going to be lower. These molecules are going to expand because they're moving with much more velocity or vigor. And that reduces the density. That's going to increase our density altitude. A decrease in density increases our density altitude, which is a bad thing. Lower temperature actually condenses the molecules, brings the molecules closer together. That decrease in temperature increases the density of the air. An increase of the density in the air is going to decrease our density altitude. That's a good thing. Okay. So it's kind of can get confusing talking about it. But if you can just remember what's happening to the density of the air, then that's how you can think through what's going on. Oh, why is it doing that? There we go. The effect of pressure on density. So same thing, guys. So higher pressure is going to be a higher density. A lower pressure is going to be a lower density. It's the same picture from earlier, but on the right side here, this would be great for us, this high density on the right side, because, or this high pressure on the right side, because all the molecules are packed nice and tightly together. You know, this means more molecules will be going into our engine in the same distance compared to this, right? That's just going to make the engine perform better. A lower pressure is going to be a lower density. So if we flew across this line right here, we may only hit, you know, 1, 2, 3, 3 molecules of air. If we flew across the same line here, we're going to hit 8 or 9 because the pressure is higher. So a lower pressure equals a lower density, which equals a higher density altitude. Worse performance. Humidity and density. So this is, humidity is the least of the 3 factors that contributes to our performance. But humidity, the way that it affects performance, water vapor is lighter than air. So when humidity is high, that air is less dense than lower humidity air. So high humidity equals low density, and that equals higher density altitude. Low humidity equals higher density and equals a lower density altitude. Like I said in class, this is Humidity is like the third distant factor when we're thinking about performance. In most, all charts, all performance charts will have you account for the pressure, for the atmospheric pressure, and have you account for the for the temperature. I've never seen a chart that like has a humidity value. So, this is more like if you're already right on the edge of the performance of what you're comfortable with, and it's 100% humidity and very humid that day, it's probably just a good idea not to fly. It's just one more thing to consider. Okay, so that's the performance section. Do you guys have any questions about that?
Nope, I'm good.
Kenneth?
No, not at this time.
Okay. Lift production. So Newton's laws, these are good to review. So the first law, body at rest will remain at rest. Body in motion will remain in motion unless acted upon. The second one is force equals mass times acceleration. And the third one is what we are concerned about. For every action, there's an equal and opposite reaction. So if you go in the PHAC, the FAA, because the PHAC is FAA sanctioned material, sanctions two separate explanations of lift. One is Newton's third law, and the other is Bernoulli's principle. So for Newton's third law, it's as simple as we fly along, the airfoil is shaped in a way that it deflects air down, and because it deflects air down, the air pushes the wing up, and we fly if you go fast enough. You can apply the same theory to the jet engine. The jet engine pushes air out the back, and as it pushes air, that exhaust out the back, that in turn, that force pushes the engine forward. Same thing with the prop, right? The prop is pushing air behind us, which is pulling us through the air. So that is the way that you can explain lift with Newton's third law. I mean, you can do this in your car, right? You're driving down the road and you put your hand out the window and you tilt your hand up and your hand wants to fly way up. You tilt your hand down, your hand wants to move down. So that's one way to explain lift. The next way to explain lift is Bernoulli's principle. So remember, Bernoulli's principle is the idea or the reality that when the speed of a fluid is increased, the pressure decreases. And remember that we consider the atmosphere and air to act as a fluid. And we can demonstrate this by a Venturi tube. So Venturi, you might remember that term from when we talked about carburetors. This is how carburetors operate on this principle also. But what happens in the Venturi tube is they have the inlet and the outlet are the same diameter, but on the inside, they have a little throat right here. What this throat creates is a choke point right here. And what it necessitates is that the air that is up here gets squeezed. And in order to make it out at the same time as the air that was in the middle, this air has to accelerate. And when it accelerates, the pressure decreases. That's what you can see on these meters right here. So the pressure's here. That looks like it's 5 and 5, the pressure and the velocity. Then as it goes through the inlet right here, through the throat, it goes up. The pressure decreases down to 3. The velocity goes up to 7. And then as it goes out, it equalizes again. Okay. So this is an observable phenomena. To me, honestly, it kind of seems counterintuitive that when you squeeze this, the pressure goes down. I understand why the velocity increases, but that's what they've,
That's what I was thinking too. Like you would think that squeezing it would make the pressure go up.
Yeah, and I don't, I think that the only answer is that it speeds up so much that because it's speeding up, the pressure actually decreases because the molecules are putting space between each other. That's got to be the only explanation. But this is an observable theory. This is true. It might be a little counterintuitive, but this is what's happening in the carburetor. This is what a carburetor does in order to pull air in and then mix the fuel in the air, vaporize the fuel in the air. And this is also, as we know, the principle that allows the wing to fly, right? So the shape of the wing is what takes advantage of Bernoulli's principle. If you were to cut the wing in half, right, draw a chord line here from the midsection here, from the leading edge to the trailing edge, you'll notice that the top of the wing is longer than the bottom of the wing. So when this air gets separated at the front of the wing, it wants to meet back here with the air it was separated with at the same time. Well, if you're going to travel a longer distance in the same amount of time, it has to go faster. Because it accelerates, the pressure decreases. Okay. So now we're back to lower pressure up here, higher pressure down here. You can think of it as the wing being sucked upwards, right? So that's how the wing works. It's the shape of the wing that takes advantage of that for us. And they can shape the wing different ways to get different properties. But this is generally the cross section of most wings looks like this. One thing to talk about here, so we've already defined angle of attack from class. Remember, angle of attack is the difference between the chord line and your relative wind. When you change the angle of attack, you also change the center of pressure along the wing. So the center of pressure is also known as the center of lift, and that is where your lift vector or your lift forces will be acting through on the wing. So when you lower the angle of attack, the center of pressure moves backwards. When you raise the angle of attack, the center of pressure moves forwards. When you stall the airplane, your center of pressure moves as forward as possible, and then it drops all the way off. It goes all the way off the back. I think you're on the commercial written, that is a written test question. So you might see that eventually. Okay. Any questions on that, on lift production, guys? Bernoulli and Newton?
No, I'm good.
Okay. So now we're going to talk about aerodynamics. And I did the first like 3/4 of this chapter. This is a long chapter. So next week, if you guys join, we're going to finish this chapter and do the next one. But first slide, we've got the 4 forces, guys. This is most of this is going to be review. Lift and weight, right? Thrust and drag. So lift and weight in level unaccelerated flight. And the FAA, this is what the FAA says. Let's go to the chapter and I'll show you what they say. The sum of all the upward forces is equal to the sum of all the downward forces. So it's right here. I don't know why. There we go. Not just lift is equal to the sum of all the downward components. And then the sum of all the forward components is equal to the sum of all the backwards components. They say this because you can see this. This is stabilized, so unaccelerated climb. Some of the lift is acting forward, and some of the weight is acting backwards as drag. I don't know, guys. That's what the FAA says. But that is, I know that's a written question on your commercial. And I think it can be on your private. I don't know if you've seen it when you've been studying or not. But so unaccelerated flight, that's what we're seeing. In accelerated flight, guys, so accelerated flight can mean you're speeding up or you're slowing down. These are no longer equal. So in accelerated flight, your thrust is going to be greater than your drag. And in decelerated flight, your drag is going to be greater than your thrust. Lift equation, guys, this is very important to remember. Like I said in class, you're never going to be given numbers or values and have to do actual math, but it's important to remember this so you can understand the different ways that you can affect how much lift the aircraft is producing. So CL, the coefficient of lift, this really is just the angle of attack. Okay. It's determined by a few different things, but it's directly related to the angle of attack and the wing shape. Remember, we can change the angle of attack. You can sort of change the wing shape, right? Using flaps, or if you have leading edge devices like slats, you could do that. On the Phenom, we have speed brakes. So speed brakes change the shape of the wing. And then we have 1/2 rho. So this is air density, right? We can't really change air density. Air density is pretty much fixed unless we're flying great distances. V squared is going to be velocity squared, so speed. And then S is wing surface area. So this is also, we don't really consider this to be something we can change. We can add flaps, and if you have certain types of flaps, it will increase the surface area of the wing. if they come back out of the wing. But you know, in general, when we're thinking about how we can adjust lift or change lift, we're only thinking about raising or lowering the nose or speeding up or slowing down. Angle of attack, guys, just a review on angle of attack. The angle created by the difference between the chord line and the relative wind. Remember, always remember, the relative wind is always parallel and opposite the direction of flight, guys. So it's not, this can be a written question for your commercial too. It's not parallel and opposite the horizon. It's not parallel and opposite the wing. If it was parallel and opposite the wing, then there would never be any angle of attack, right? So your direction of flight is going to determine where the relative wind is. And that is why we can stall at any airspeed, right? I think on the next, I didn't put it in here. They're showing on this, they show a dive. I think I put it in later about stalls, but we'll just talk about it right now. And then we can skip later because I'm on the tangent right now. Jeez. I told you this was a long chapter. So think about in a dive here, guys. You have all this momentum going downwards. And if I yank the plane upwards, I'm going to get an elevator response that raises the nose, but the airplane's still traveling downwards somewhat, right? So now we've just increased the angle of attack, you know, tenfold. And, you know, we're at this point, we might be going 150 knots. But if we yank that nose up, well, you're still traveling downwards for the most part. And you're going to be exceeding the critical angle of attack. So now you've pretty much killed yourself, you know, depending on how low you got, because you're not going to be able to recover this stall quickly enough. So if you get into a bad dive, for some reason, you get disoriented or something, you need to be gently bringing the nose back up if you don't want to stall or break the airplane.
So you're saying the movies don't accurately portray flight properly?
Well, I don't know. Yeah, it all depends on technique, I guess, and the wherewithal of your airplane, right? Because fighter jets and, you know, World War II fighter planes could deal with this somewhat, but those guys also had a lot of training, right? So they knew the exact amount of, you know, back pressure they can give it in a dive and what can keep you flying. It's more, I think, honestly, if it's one controlled movement, you're going to be okay. But if you yank it, snap it, like if you just panic, pull full back, yeah, you can throw the nose right up and the airplane's gonna stall on you. Lift over drag ratio. This is something we did not talk about in ground because you can get into the weeds a little bit with this, but we're going to talk about it in here because I think it's important to know. And you will, on your commercial, end up getting questions about this. But the lift over the drag ratio is the amount of lift divided by total drag. Okay. The L over D max corresponds to your best glide angle of attack. The best glide angle of attack for trainer airplanes is around 10 to 12 degrees. In the newer airplanes, if you have an angle of attack sensor, they can demonstrate that to you. And they'll actually show you in the POH, you know, what the best glide angle of attack is. But for us, for the older airplanes that we have, you know, maintaining your best glide speed is what corresponds to the best glide angle of attack. This right here, guys, you're going to start seeing this a lot. Okay. This is the lift over drag chart. So what we can see here on the left is the coefficient of drag. Then we have the coefficient of lift right here. We have our corresponding angle of attack along the x-axis. And then we have the lift over drag value right here on the right, the furthest right y-axis. This curve right here is your lift over drag curve. You will get questions about this on your commercial written. Your lift over drag max right here on this chart is about 6 degrees angle of attack. So this is where you would be on this airplane, maximizing the amount of lift for the least amount of drag. You'll see here, this curve right here is the coefficient of drag, and this curve right here is the coefficient of lift. This lift over drag max corresponds with the point at which the distance between these two lines is the greatest. That should make sense, right? Because it's just this red line divided by this orange line and the value of that. What happens, as you can see here, as you go along the coefficient of lift max, you're increasing your angle of attack down to here. Your coefficient of lift is increasing. And then the second you go further than your coefficient of lift max, your maximum coefficient of lift, your highest angle of attack, you stall. Okay. So right before your critical angle of attack is actually your highest coefficient of lift. And that, I mean, that should make sense, right? The highest that I can pitch the airplane up and not stall, I'm getting the maximum amount of lift out of it. Once I go past that point, I'm stalling, and you can see the line drops off rapidly, right? Because you're no longer producing lift. So this is a chart that you will get questions about. Sometimes they just don't have anything labeled, and it'll ask you, you know, label A, and it'll be lift over drag max, something like that. Okay, so this is right out of the PHAC. So next we'll talk about drag. So drag, guys, is going to be the combination of all forces that work to slow down the aircraft. There's two general categories of drag. You have parasite drag and induced drag. Induced drag, guys. Induced drag is drag that is created as a byproduct of lift. Induced drag decreases, so the total amount of induced drag decreases as speed increases. That's a written test question too. So induced drag, the whole, you know, this comes from Newton's laws, right? You can't get anything for free. You know, we create lift, so we have an opposite reaction, which is induced drag. This right here is the total drag curve, and it's showing you the relationship between induced drag and parasite drag. So the slower you have your airspeed down here, the slower you're going, the more of your total drag, which is the dotted line here, is produced by induced drag when you're slow. The faster you get, the more your induced drag goes down and the more your parasite drag goes up as contributing to your total drag. So when you're going very fast, you're not incurring a very big penalty from induced drag. Most of it or all of it is coming from parasite drag. Wingtip vortices. So wingtip vortices are the same thing as induced drag. These are the result of the high pressure air below the wing wanting to, or the high pressure air below the wing spilling over the top of the wing in pursuit of the low pressure area. So this is just that whole idea that in nature, pressure wants to equalize. So some of the air that's down here below the wing, and this happens not just on the wing tips, but happens all the way along the wing. Some of that air is able to spill over to the top of the wing. And you can think about it as pressing down on the back of the wing, and that creates drag. So when we're flying very slowly, a lot of this air has the ability to get up on top of the wing and push down on us and create drag. Okay. The faster you fly, and this is just the way that I think about it, the faster you fly, the less of that air is able to quote unquote catch up with the wing and push down on that wing. You also hear this called downwash, okay, when they talk about it. Same thing. So the slower an aircraft is flying, the more it affects it. What this is also showing here, guys, is ground effect. So I don't think I put a slide. Oh, I did put a slide in here. So what ground effect is, guys, is a significant reduction in induced drag due to ground interference. So what's happening here is as you get closer and closer to the ground, those vortices, those wingtip vortices or the induced drag doesn't have enough room to get back up around onto the back of the airplane. Okay. And that's why you feel a cushion or, you know, a sudden increase in lift. You know, it's not technically an increase in lift. It's a significant reduction in induced drag. Remember, guys, this takes place within one wingspan of the ground, and it's an exponential occurrence. So the closer you get, the amount of ground effect you get increases exponentially. I think like some crazy number, like 60 or 70% of the ground effect is within 1/3 of your wingspan between the ground. So start coming in fast, guys. This is why you float really long. That ground effect, you reduce all that induced drag, and now you just got your lift to drag ratio is really high. Okay, Parasite drag, guys. So there's 3 types of parasite drag: skin friction, form, and interference. These are all straightforward. So skin friction is literally just drag due to friction, right? We cannot make a perfectly smooth surface. There's going to be friction on the aircraft. Interference drag, guys. Interference drag is caused by the convergence of airflows along the aircraft. So when you fly, you get air that sticks along the fuselage here and creates its own kind of like stream, and you get air that obviously sticks over the wings. And when those two come together, they're at different angles, and they will create eddies and create turbulence and drag. So the airplane manufacturers try to do their best to smooth these confluences out. That's why you see wing fairings, and you'll see fairings on the places where things, different airstreams will intersect. Form drag is just, how aerodynamic is something, right? So you can see here a flat plate, not very aerodynamic, creates a lot of drag. A sphere inside a housing, which is basically the wing shape, is our best bet here. So obviously we're always trying to make airplanes as aerodynamic as possible, and they're starting to try and make cars more aerodynamic, more fuel efficient. Wake turbulence, guys. This is a big thing. This is one of the big things in ground school that actually ends up being applicable to flying. Yeah, Kenneth?
So going back to that last slide,
Yep.
so how you're saying, like with cars being more aerodynamic, especially the electric ones, they're all flat more now on the front.
Yeah,
Like,
exactly.
I never understood, like, how is this more aerodynamic when things are getting boxier and
Yeah.
not,
I think they're
rounded as
valuing-
much?
I think they're valuing the look over the function.
Yeah, that's what
Yeah.
it seems like. I'm like, this is a complete opposite of what you want.
Yep.
So, okay, so it's not just me noticing the stupid designs they're doing. Okay.
Yeah. All right. Wake turbulence, guys. Like I was saying, this is actually practical. It's good to know this stuff. So wake turbulence is created by all aircraft, and we're mainly concerned about wake coming from aircraft much larger than ours. So like if you're in a 172, you're not worried about other trainer airplanes, even like an Aztec or like small piston twins. Once you start getting like a Beechcraft or something like a King Air, yeah, you're going to be concerned about that, mainly because they've got those big props that are spinning and turning up a bunch of air. But wake turbulence, guys, is just induced drag. It's the same thing. So wingtip vortices, wake turbulence, same thing. Wake production. So we talked about this in class, but it's good to review. Wake is only produced when the aircraft's wheels are off the ground. So when we're trying to consider what actions we need to take to avoid wake turbulence, when you're taking off behind an airplane that's landing or taking off behind an airplane that's also taking off, if you can remember that the wake only begins to be produced when the aircraft's wheels are off the ground, you can think yourself through, should I be taking off after where this person landed, or should I be taking off before where this person landed? The 3 things that affect wake, or that make wake production the greatest, is when the aircraft is heavy, clean, and slow. Okay. This is because in all 3 of these instances, the aircraft is going to have a higher angle of attack. The heavier the airplane, the more lift they need to produce. So they need to raise the nose. When an airplane is clean, so no flaps really, it necessitates a higher angle of attack because flaps allow us to fly at a lower angle of attack at slower speeds. And then when an airplane is slow, you need a higher angle of attack, right? Because you're not producing lift from your airspeed, so you need to pick the nose up. So those create more induced drag, which is our wake turbulence. So wake avoidance is pretty simple. When you're flying along in cruise, you want to stay above the flight path of aircraft that are much higher than you. And then if you can't be above them, you want to be at least 1,500 feet below them. because wake will sink, and it can exist for a few thousand feet. Now it will dissipate as it drops, like it will get less intense, but there have been accidents. There's a famous famous accident where Citation 10 flew below 747 and it flipped them over. And I can't remember if they broke up and crashed and died or if they just flipped over and everything was fine. But yeah, so this really is ATC's job. They do have wake turbulence like limits and distances that they're supposed to follow for you. But obviously it's still on you to make sure you feel safe. This is just showing the wake, ending when they touch down and beginning when they rotate. So if we were taking off and this airplane just landed, we want to take off beyond where they landed. If we're taking off and this airplane just took off, we want to take off before where they took off, and we want to outclimb them and not follow them. Or what's more likely, we're not going to outclimb the jet, is turn away from their flight path as soon as we can. So rotate before them and get out of their flight path as soon as it's safe, because you do not want to be riding through this. It can cause an accident and can, especially close to the ground, can kill you. Oops. So what can happen? This is another written question. Is the most dangerous time for wake turbulence is going to be a light crosswind. What that does is the vortice that is upwind or in the wind can be kept over the runway for a longer time. So what this means in practicality is, so if you have a light wind, what you should do is after an airplane that is much larger than you lands, is you should observe at least 2 minutes before you take off. If you're at a towered airport, tower will do this for you most of the time. Sometimes they may not be paying full attention and try to clear you. At that point, you should ask them if you can wait a minute, or not even ask them, tell them you're going to wait a minute. And if they
That is
get all,
a practice question that I've had
yes,
where they talk about like you're on this, like actually it's opposite runway, like it's like an X kind of setup. So it's like the one jet goes after, and it's like, oh, it's got this much wind. Like, where's it going to be? And it's exactly what you're talking about, how it's going to just blow into where the little plane needs to take off at.
yeah, exactly. So, yeah, don't be afraid to take authority in that situation. Tell them you want to wait, another minute or so. Okay. Stability, guys. So there's two categories of aircraft stability. We have static, which is the initial tendency of the airplane, and dynamic, which is the tendency over time. So this is what the airplane's going to do if it's disturbed from its equilibrium. So if we have positive static stability, if the airplane gets disturbed, or in this case, the ball gets disturbed to the right, it's going to swing back to the middle. That's going to be its initial tendency, is to come back. Neutral static stability is if the airplane gets disturbed, it's just going to stay in the position in which it was disturbed to. So if it gets pushed to the right, or you get pushed into a right bank, it's just going to stay in whatever right bank it got pushed into. Negative, which is the worst, negative static stability, is its initial tendency is if, let's say, you get pushed into a right bank, it's going to keep banking right if you don't do anything about it. Dynamic stability is your airplane's reaction over time. And as you can see here, a positive static stability, if the airplane gets disturbed, it wants to go back to its equilibrium. So it'll dampen those oscillations until it eventually goes back to normal. Neutral dynamic stability is going to be over time. The airplane just stays in that same oscillation, just keeps going up and down, but it's not getting worse. Negative dynamic stability, once again, is the worst of all. If it gets disturbed, it begins to oscillate and the oscillations get bigger. So that's what negative dynamic stability is. So remember, static is the initial tendency. Dynamic is the tendency over time. For both of them, positive is going to be the best outcome, and negative the worst. Is this the last slide? We're getting pretty close. So next thing, guys, we didn't talk about this in class, but this is good to know. Dihedral. So dihedral is when you construct a wing, as you can see on this slide, to have a at a, what do they say, positive degree slope from the wing to the root. Why they do this is it's a stabilizing technique. What can happen is you can get a gust and it induces a roll, creating a side slip. When you get a side slip, now all the air, because the airplane is flying with the nose crooked, your relative wind is all on this wing. What the dihedral does is, because this part of the wing is higher than the root, it has a higher angle of attack. So it starts creating more lift, and it will raise the wing back up, giving the airplane, or making the airplane more stable. The airplane will naturally right itself to a point, right? If you get a really, really big gust and you're put into like a 60-degree bank, you're going to have to use some control input. But this is why a lot of times if you get you catch a gust or something, you don't even have to react. The airplane will right itself, because it has the correct amount of dihedral. You know, the 172s actually have a little bit of dihedral. It's way easier to see the archers and the arrows. It's very obvious, but even the 172s have a little bit of dihedral. You can also have anhedral. So you can see this on the big tanker military planes. What this does is it actually helps them turn better as they, it just promotes a roll. I can't really explain it too well to you, but that's why you have anhedral. It's because they're bigger and heavier. It just helps those, their control surfaces might not be as big as they need to be. So they have anhedral to help them. Turning flight, we talked about this in ground, but it's always good to constantly go over these guys. So in level flight, right, our lift is acting straight up and our weight is acting straight down. When we want to make a turn, we need to trade some of our vertical component of lift for horizontal component of lift. What that does is now the resulting lift vector is out here, and the resulting load factor is this way. Well, what has happened is we've traded some of this vertical lift for horizontal lift. What's going to happen if we don't change our angle of attack or our speed? We're going to descend, right? So we will pull the nose up in this turn in order to stay at the same altitude. This is why our stall speed increases in a turn, right? Because we have to increase our angle of attack. As you can see on the right, on the steeply banked turn, the more, the steeper the bank, the more vertical component of lift we have to exchange to horizontal component of lift, meaning we have to raise the nose more, right? Which puts us closer to a critical angle of attack, which increases the stall speed, which is not a good thing. Okay. The load factor that we're getting is due to centrifugal force, right? When you turn, you also have a resultant force right here, which is, they call centrifugal, which is pulling you away from the turn. That's why your resultant load ends up at a 45-degree angle to your weight, or exactly opposite of your total lift. All right, stalls, guys. This is something I beat to death with everybody that I teach. So like I've said multiple times, stall occurs when the aircraft exceeds the critical angle of attack. When this occurs, the boundary layer is separated from the airfoil and lift is no longer sufficient to support the aircraft. Lowering the angle of attack will fix the stall. Stalls have nothing to do with airspeed, okay? The only reason we talk about stall speeds is because that is the best representation of your current angle of attack in the airplane. If you don't have an angle of attack indicator. What I mean by that is the manufacturers went and test flew the airplane, and they found that if you are maintaining your altitude at this airspeed, the only way for you to do that is to be pitched up high enough that you're going to stall. Does that make sense? if we were able to have angle of attack indicators in the airplane, you could look at that and see if you're going to stall and not have to use airspeed to determine if you're going to stall. The only reason I'm stressing this is because you need to know that you can stall at any airspeed, like our demonstration that we talked about earlier, if you exceed the critical angle of attack. Okay, that was the last slide. But that's the important part when we're talking about stalls. You can see here, this is a load factor chart, which I think you get in your, you might see in your, on your written. As your load factor increases, which is corresponding to your bank angle, your stall speed increases exponentially, right? So the more you bank, the more you need to raise the nose, the more load you put on the airplane, the higher your stall speed is going to be, which is not a good thing, guys. We do not want a high stall speed. So I didn't prepare the rest of this because I thought this was going to take longer than it did. So we'll go over this stuff next week and do chapter. Let's see what 6 is. We could probably get away with doing chapter 6 and 7 also, because we don't really need to talk about the flight controls too much in depth because they're not that important to what you guys are doing. Do you guys have any questions for me? Anything about your written or anything?
I think I'm good.
Kenneth, got anything for me?
Not really, because I mean, like I said, a lot of them were at first I had, a question, and then, it was either, like I said, I knew what I was doing and just, I don't know what I did,
Yeah.
something else got brain and I did, some other kind of thing, or, just, yeah, I figured out, what it's talking about and it makes sense kind of thing. So
Okay.
it's just, yeah, just more seeing it kind of stuff. It's like, okay, then I do remember it, but yeah, some of them I just mix up, you know, uh, a question from another question kind of, that's similar.
Yeah.
So that's what it seems like. It's not like I don't know, but it's like, okay, like this was similar to another one. Like, oh, I know this one, and like, oh, wait, it was this one. Whoops. Uh, So just mixing them up, kind of thing.
Okay.
So, but like I said, overall, it doesn't matter. I seem to even some, like I said earlier, like where I didn't have had some new questions pop up, and I'm like, I've never seen this, and some I got completely right, and others I'm like, I was kind of close. I just chose the the one that was, close to the answer, that trickery one.
Yeah.
So just close enough one is what I picked. So I'm like, I guess it could be worse because I didn't choose the completely wrong one. So,
Yeah. I've got you. Okay.
but yeah, I mean, and then just some of them where it's like, I did one earlier. It was doing I forget what it was for, but the math. I'm like, oh, it's 72.2. Like, no, it was 73.3. I'm like, you got to be kidding. Like,
Yeah.
I mean, it was trying to figure out like the load, if it's normal or utility. I'm like, both of them are normal. What does it really matter at that point? I
Yeah.
mean, that 1.1 is gonna make or break your flight. Like, but
Yeah.
it wasn't even close to being, neither one was close to the utility anyway. So I'm like, just make a different number then. Like, I don't know how, because if that's what aggravates me, I think the most, because it's like if you're not exactly perfect, you get the answer wrong. I'm like, no, at least I know it should be more about I know what to do. I know what
Yeah.
I'm doing. It's just you want too much of a minuscule, number difference.
Yeah. That's the
So
frustrating thing.
yeah,
So,
I think that's what gets me the most aggravated. I'm like, this is right. I did this, and I thought I was pretty precise when I'm like, okay, and I'm counting like 1, 2, all right, that's looks like 13.5 because it's not right in the it's on the line, it's like in the middle, and it it must have been 14, I'm guessing. It was something like that, like whatever. But and like I said, in the end, I felt comfortable. At least I knew what I was doing to get essentially close enough to the right answer. So I just hope it won't be like that tomorrow where I'm like, damn it, I missed this because of the same kind of, reasons. But obviously we don't get told after. So, but
Yeah. All right. Well, shoot me a text tomorrow when you guys finish. I'm sure you're going to be
Okay.
fine, but let me know. Let me know how it went.
yeah,
I'm
Gus said
excited to
I should be done
hear.
at 2:30.
Yeah, I have
I
complete faith that
I
you
told
guys.
him I was like, I at least like at most take an hour, probably. So
Yeah.
I mean, it just really depends on how many questions. Like, oh yeah, yeah, yeah. He kind of broke it up. He's like 50% you're just gonna know. I think another like 20 or so percent. He's like, you're gonna have to like think about, and then like there was like a 10%. He's like, you're just gonna have no clue, and you're just gonna guess.
Yeah.
So, but and I think he had maybe like 10 questions where it had like pictures and diagrams and things like that. So. I feel comfortable with most of that stuff. I mean, I think some of the stuff where people were, like I feel real good on VOR stuff. I mean, especially making that little, um, I don't know, the little picture thing. That that even works when there's no to or from. So that's what I think is even great about it because I had a question and like I put the little thing on there and I was like, okay, and I was like, okay, there's no to or from, but it looks just like this two over here because and it was right. So I'm like,
Yeah.
honestly, I don't have to know anything. If you just have that little picture and line it up, it does it for you. So, but yeah, I mean, majority of this stuff, like I said, I feel I'm really good at the vortices and stuff. Like they actually was kind of funny is Sporty just had a little thing this weekend that like quizzed that, and I got 6 out of 7. The one I didn't know was where it was like the in regards to like where it's coming off the wingtip or something. I'm like, I don't know, but it was all the other stuff about flying portion, like what where it would go, and so to me the more important stuff.
Yeah.
So, but yeah,
All right, I gotta roll. I'll text you tomorrow though.
Okay.
Kenneth, I'll see you tomorrow as well. So
yeah. So maybe depends on how quick or slow either one of us is. Maybe we'll see each other after.
all
All
right,
right.
see you guys.
See you guys.
Okay. All right. Bye.